Hello, we're going to do lesson 5.3 today. Trigonometric functions on the unit circle. First thing that we need to do is talk about what exactly the unit circle is. So as you can see here, I have the unit circle defined as a circle of radius 1. Now, when we're talking about the unit circle, we usually place the unit circle in the coordinate plane, and we place it where it's centered at the origin. So this point right here is the origin, 0, 0. So the circle is centered at the origin, 0, 0. Now it has radius 1. That means that it's going to hit very specific points in the coordinate plane. We look to the right here. If we go out to the right, this point right here would end up being 1, 0, 1 unit away from the origin. And this point directly north of the origin, okay, that's going to be 0, 1. And if we go out to the left, this point over on the left is going to be negative 1, 0. And directly south of the origin, this point would be 0, negative 1. Okay, so we've defined some very specific coordinates, and actually those are the quadrantal angles that we mentioned before. Again, that's any angle that lands on the axes, some multiple of 90. But more significantly, there are other points that we could define. As you can see, I have another line drawn here that goes out to somewhere in the middle of the first quadrant. Now, I'm not exactly sure where that point is located. I know it's 1 away from the origin, but I don't right now know where it is. So we can just label that random x, y. All right, so how does this tie into trig? Well, in order to talk about trigonometry, then we need to talk about an angle. So as you can see here, this line that I drew and the line that would be the x-axis forms an angle which we can call theta. Okay, Greek letter theta. And now we can start talking about this in terms of trigonometry. Actually, if we drop a perpendicular from the dot straight down, we would end up getting a triangle. And we talked about our trig functions, sine, cosine, and tangent, in terms of a triangle when we defined them. So let's talk about sine, cosine, and tangent with this regards to this specific theta. So we know that the horizontal is x. Okay, that's what we defined it as by this point, and we know the vertical is y. Okay, and that's where this xy came from, this point. Okay, this random point. We're not sure exactly where it's located. We know it's located at a horizontal distance of x and a vertical distance of y. So if we can figure out what those two are, we can define what sine, cosine, and tangent are. So specifically, let's talk about sine right now. Whoops, got a couple little glitches there. Clean that up. Go back to blue. Okay, so we're going to talk about the sine of theta. Okay, well, SOHCAHTOA tells us that the sine of theta is the opposite over the hypotenuse. So talking about the unit circle here in theta, the opposite side would be y, and the hypotenuse would be 1. Well, simplifying that, we can actually say that the sine of theta is defined as the y. The cosine of theta is adjacent over hypotenuse. So the adjacent side is x, the hypotenuse is 1, so we can define cosine as x. So this is very significant because now this random point that we were talking about out in the middle of nowhere, actually, if we know the value of that, we can actually tell you what the cosine and sine are without doing any work whatsoever. The x-coordinate of any point on the unit circle is the cosine of the angle formed, and the y value, let's try again, will be the sine of theta. So if you know any of the coordinates, right now we actually know 4 of them. We know the coordinates of this angle, the vertical angle, which is 90, the horizontal, which ends up being 180, and the downward angle here that would form 270 as we work our way around. We will actually start to be able to talk about the quadrantal angles, and we know the sine and cosine of them using the unit circle. And if we have an angle that is not on the unit circle, that's not on a quadrant, is not a quadrantal angle, it's not on the axes, then we can actually create a triangle and find where that point is at, and then we would know that the horizontal distance is cosine and that the vertical distance is sine. So we can start actually talking about sine and cosine of any angle. And what this does is this allows us to extend our knowledge of sine, cosine, and tangent past 90 degrees, because everything we've been dealing with so far has simply just been within a triangle. So this allows us to open up to many, many, many more angles. All right, so let's go ahead and start doing that. Let's take a look at some examples here. Okay, so here you can see that we want to use the unit circle to find the cosine of negative 180 degrees. So let's talk about negative 180 degrees here. So I'm going to draw a little circle. Let's try to. Computer's been acting up a little bit. Okay, so here we go. We have a circle, and I put in the coordinate plane so we can talk about the unit circle, radius 1. And we're going to find out where's 180 degrees negative. Well, if we start here in the standard position on the positive x, and we measure over in this direction, the negative direction, this is the angle of 180 degrees in the negative direction. Okay, negative 180. So if we know this point on the unit circle, which we do, we know it's negative 1, 0. We can solve for the cosine of negative 180 degrees. So the cosine is the x coordinate. So the cosine of negative 180 degrees is simply just negative 1. Okay, let's take a look down here at problem B. Now it says the secant of 90 degrees. Well, we can talk about 90 degrees. Again, let's go ahead and draw a circle. Okay, so 90 degrees would be from the horizontal x to the vertical y. That's 90 degrees. Okay, 90 degrees. So where would we be hitting the unit circle? We would be finishing right there on that dot north of the origin. So that's going to be 0, 1. Okay. So now that we have the coordinate, now we need to figure out what exactly does secant mean. Well, from the last lesson, we know what the secant is. Okay, the secant is 1 over the cosine. So if it's the secant of 90, then this is going to be the 1 over the cosine of 90. Okay, so 1 over the cosine of 90. So we can figure out the cosine is. Again, the cosine is the x-coordinates, So we're going to plug 0 in here. So 1 over 0, and that's not a good situation. We never want to divide by 0, so this is going to be undefined. So the original secant of 90, okay, whenever we start graphing the trig functions, you're going to see that there is going to be, if you remember any undefined situations before we talked about graphing, there's going to be a vertical asymptote, okay, on the secant graph at 90 degrees. So when we get into graphing that later on, we'll know exactly what to do when we run into that situation. Okay, but right now, we just need to know that it's undefined. Okay, let's try another problem. So use the unit circle to find the values of the 6 trig functions of 135. Okay, so let's first define the angle, 135 degrees. That says unit circle again, so let's go ahead and get that circle. 135, drawing in standard position. 135, well, that's 45 more than 90, so that's going to be out in this direction, 135 degrees. Okay, now, we are not on the quadrantal angle. We are hitting the unit circle out here in the middle of nowhere. So what we're going to do is we're going to drop a perpendicular, and we're going to try to create a right triangle that we can solve. I'm going to make this a little bit larger over here so it'd be easier to see. Okay, so that's this triangle right here. So we need to talk about the reference angle. So that's the distance from here to here. Okay. So that would be this angle here. So what's the distance from 135 to 180? I'm a little trouble with this. Switch to blue. So 135 to 180. Well, that distance is 45 degrees. So this angle right here, okay, would be 45 degrees. Okay, which makes this angle 45 degrees. Okay, if we know that this distance here, the hypotenuse, is 1, then we should be able to figure out what x and y are. We're going to use a little formula that we know from geometry, Pythagorean theorem. So for our problem, we're going to get x squared plus y squared equals 1. Actually, that's not the case here, because what we can do is we can actually say that these are the same. X squared and y squared are the same, so we can say x squared plus x squared equals 1, or 2x squared equals 1, or x squared equals 1/2. Solving for x, we get x equals plus or minus the square root of 1/2, which ends up being 1 over the square root of 2. Getting rid of the radical 2, we get x equals the square root of 2 over 2. So for our triangle, our x and our y are both going to be the square root of 2 over 2. Now, the direction does matter here. We are in the coordinate plane. So this was where the origin was. So we're moving in the left direction, so the x is going to be negative. That's where that plus or minus comes into play. So one's going to be positive, one's going to be negative, and the vertical is going to be positive. So this is going to be positive plus square root of 2 over 2. We don't need to put that positive, it's understood. Okay, so we now know the x and we now know the y. The coordinate here, okay, this coordinate, this x and this y, is going to be negative square root of 2 over 2, and this is the square root of 2 over 2. So that's the coordinate, the point, okay, that shows up when we have 45 degrees. Okay, 135 gave us the reference angle of 45 degrees. So now that we know that, we now know the cosine, and we now know the sine of these. Now we need all 6, so let's go ahead and say the sine of 135 degrees. Okay, well that's going to be the y value, the square root of 2 over 2. The cosine of 135 degrees, that's the x, that's negative square root of 2 over 2. Okay, now the tangent of 135 degrees, okay, is going to be sine over cosine. So I think you can do the math pretty quickly here. We're going to get negative 1. So we're simply going to take the sine and divide it by the cosine to get the tangent. So anything over itself is 1, and it's negative. Okay, let's go ahead and put in the reciprocal functions now. So the reciprocal of sine is cosecant of 135 degrees. I'm just going to make some room over here. Okay, so the cosecant of 135, actually, let me switch that to blue. Okay, that's just going to be the reciprocal. Now that's going to be 2 over the square root of 2, getting rid of the radical 2. We end up with 2 square roots of 2 over 2, or simply just the square root of 2. The secant of 135 degrees. Again, we're reciprocating this. Now we just did this work for the previous one, except it was negative. So we should end up with negative square root of 2 as our result. And the tangent, cotangent, reciprocal of tangent is cotangent of 135 degrees is going to be, well, the flip of negative 1 is just negative 1. Okay, so there's your answer to the 6 trig functions of 135 degrees. Now that we've established 45, though, we used the reference 45, this point is quite significant. And you're actually going to find that 45 degrees, okay, ends up using the point the square root of 2 over 2 and the square root of 2 over 2 every time. So some reference of 45 degrees, okay, is going to use this point, this significant point of square root of 2 over 2, comma square root of 2 over 2. Now that will change depending on the direction. As you saw here in ours, 135 was over in quadrant 2, so the horizontal was negative and the vertical was positive. So if it was in quadrant 3, they'd both be negative. If it was in quadrant 4, it'd be the opposite of what we had. We had positive square root of 2 over 2 and negative square root of 2 over 2. All right. Okay, how do you find trig functions of theta when given a point that is not on the unit circle? Well, that's an interesting question. So if we have the unit circle, and what if we have just some random point out here in the middle of nowhere, not actually on the unit circle? Well, the funny part is you don't do anything different, okay? You still are going to connect it to the origin. We're still going to draw our standard position. We're still going to create a theta. Okay. Now, if you can, not liking the red tonight. So if you can figure out where this point's at on the unit circle, you could do that. But if we have this point, if we have x and y, if we know what that is, we can actually just go ahead and put it here. We'll get an x, we'll get an get a y. So we'll have the x and y, because remember, we have a given point. Then all we got to do is now find this new hypotenuse, right? Let's call it r. Okay, so it's some other radius of a bigger circle, not the unit circle, but of some bigger circle. We can still use the basic SOHCAHTOA, though, and just use opposite adjacent hypotenuse. We can use x, y, and r. Okay, so we can just revert back to what we already know from SOHCAHTOA. So we don't need to figure out the actual point on the unit circle to do that. All right, so let's go ahead and put that into effect. here we have an example. We want to find the values of all 6 trig functions for theta in standard position if 5, -12 lies on its terminal side. So there's our given point. That's where the angle will end, at 5, -12. So we're going to have to draw a little bit more accurate of a graph here. Okay, so 5, -12. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's 5, -12. Then quadrant 4. 5, -12. All right, so we're going to go ahead and draw this to the origin. And then we're going to draw the perpendicular to the x-axis. So here's our angle. Try green, see if that likes us. So the angle that we're talking about is right there, theta. So that's the angle we're interested in. Or you could say theta's out here. We usually put it inside of the, they end at the same place, so they're going to be the same angle. It's no matter whether it's positive or negative. So there's our theta. We have x, we have y. We just need to know this hypotenuse, okay? So x is 5, y is -12. We need to know the hypotenuse. Let's call it r. So again, the Pythagorean theorem will come into play and help us here. So x squared plus y squared will equal r squared. Plugging in what we know, we'll have 5. What's doing with that? 5 squared plus -12 squared equals r squared. So that's 25 plus 144 equals r squared. 169 equals r squared. And the square root of 169 is 13. So we know that r is 13. We know our x, we know our y, or you could say we know our opposite and adjacent. We know the hypotenuse. We can now do all 6 trig functions. So the sine of theta, we don't know the actual angle. So the sine of theta is going to be the opposite over the hypotenuse. It's going to be -12 over 13. Okay, cosine of theta. Okay, it's going to be our adjacent side now. Okay, this is our adjacent. Okay, over the hypotenuse, so that's going to be 5 over 13. And tangent of theta is going to be our opposite, -12 over our adjacent 5. Looking at the reciprocals, cosecant is going to be -13 over 12. Remember, we're just reciprocating the secant, 13 over 5, and the cotangent, -5 over 12. All right, so there's our 6 trig functions. So if you have something off the unit circle, don't worry about it. Just go ahead and revert back to your regular SOHCAHTOA trig functions. and you'll be just fine. Okay? So, here we go. We have, pretty sure, one last problem. Yep, last one. Okay, we are given a trig function. We're told what quadrant theta is in. We need to find the other 5 trig functions. Okay, so let's go ahead and first set up our coordinate plane and put an angle in the correct quadrant. So he says we're in quadrant 3. So I'm going to start in standard position. I'm going to create an angle out here in quadrant 3. Alright. Now, we know that the sine of theta is negative 4/5. Okay, so what we can do here is we can create a right triangle. List theta. And now we can talk about the sides in terms of opposite and hypotenuse for sine. So opposite over hypotenuse. So the opposite side would be negative 4. Hypotenuse is 5. What we can now find is the adjacent side. Okay, let's call that x. Okay? Because if we were talking about a point out here again, we would not know what x is. We would know what y is. So we'd have x negative 4 as our point. So if we can find that x using Pythagorean theorem, we will know all of the sides. And once we know all the sides, then we can find all the trig functions. So let's go ahead and do that. So we're going to have x squared plus a negative 4 squared equals 5 squared. So x squared plus 16 equals 25. X squared equals 9. So x equals plus or minus 3. Now that depends on the situation. If you look at ours, quadrant 3, we need a negative 3. Okay, so we have our opposite. Our opposite is negative 4. We have our adjacent at negative 3. And we have our hypotenuse here at 5. So we can now go through all the trig functions. Now the sine was given. We'll rewrite it. The sine of theta was negative 4/5. The cosine of theta. Okay, if we look here, the adjacent is negative 3. And the hypotenuse is 5. And the tangent of theta okay, opposite over adjacent, that's negative 4 over negative 3, or 4/3. Reciprocal functions, the cosecant of theta going to be negative 5/4. The secant of theta, negative 5/3, and the cotangent of theta, 3/4. Okay, so that's it. That's the 6 trig functions of theta. So if you're given a single trig function, you can use your knowledge of SOHCAHTOA. You'll know 2 of the sides, and then find the third using Pythagorean theorem to find the rest once you have the third side. So that's it for today. We will see you next lesson.